One of the interesting things we can examine using the Huckel method is the energy stabilization that one gets from having a conjugated pi system as opposed to one that's not conjugated. Now, how would we get a handle on this? Well, first of all, let's draw what a conjugated pi system looks like. It's a series of alternating single and double bonds between carbons along some chain, and it could go, for some distance in either direction. All right, so what we're interested in is there something special about the fact that these have been arranged in alternating single and double bonds? And what we want to compare it to, in some sense, is the energy that we would get just from having double bonds, but not necessarily somehow connected to one another. So each one of these is almost like a small ethylene fragment. And what we would want to do is compare the energy of this fragment individually taken versus the energy of this whole system when the electrons somehow are enabled to interact with one another. All right, so in order to get a handle on this, let's calculate using the Huckel parameters what the energy levels would be for ethylene itself. All right, so what we would have is a secular determinant that is a 2 by 2 determinant. There are 2 carbons here, and it's a fairly simple 2 by 2 secular determinant. It looks like this, and that's equal to 0. So when we work this out, this is alpha minus E squared minus beta squared, and we can solve this for the energy, and we find that the energy is equal to alpha plus or minus beta. Now, I will make a point that, in fact, we have 2 energy levels here. One is alpha plus beta, which is the lower one, and it's the lower one because beta is a negative number. But you'll notice that they are equally spaced about energy equal to alpha. Okay, one energy level is higher, one is lower. Energy of alpha is the energy of a p orbital that is not participating in bonding at all. So in some sense, this represents sort of a center of gravity for these molecular orbitals that are being formed. Okay, so how can we compare an n-atom linear polyene with some number of ethylene molecules to get an idea of how much energy stabilization we get from the electrons along the chain? All right, well, let me first indicate that if we have n atoms in our chain, this means that we must have n p orbitals. Since each p orbital, I should have made that a capital N, since each p orbital contains one electron that contributes to the pi system, this means that we have a total of n electrons in our pi system. All right, so when we begin putting these orbitals together for a linear polyene, and again I'm going to draw the same sort of figure that I drew over here with alpha being the midpoint. All right, this alpha represents sort of the non-bonding level for these various p orbitals in this chain. Now what we would find for a linear polyene is that the energy levels, and this formula up here verifies this, these energy levels are going to be spaced in such a way that for every one below this line, there's one above the line by the same amount. So we'll have pairs of energy levels, one below and one above the line for this linear polyene. Now I've drawn this for a total of 6 molecular orbitals, so that means there would be 6 atoms in this chain, but there of course could be much more. All right, when we fill electrons in, we're going to use the Pauli principle, just as we did for atoms and for diatomic molecules. And so in this case, we're going to have a total of 6 electrons, as it's drawn here, but we're going to have a total of n electrons, and they will totally fill the lowest n over 2 of these molecular orbitals. So this is a total of n over 2 molecular orbitals. The other n over 2 are up here. Okay, and it makes sense that half would be energy stabilized, half would be energy losing, if you will, from that molecular orbital combination. So what we want to do is find what is the total energy for these electrons and compare them to the same number of electrons in ethylene molecules with these energies written over here. All right, so for the polyene, and I'll write that as E poly, I'm going to have a total of n electrons, but they're going to be filling n over 2 molecular orbitals. So I'm going to have n over 2, 2 electrons in each orbital, times alpha, and this is going to be plus 2n times beta, with a sum from n equals 1 to n over 2, because we're filling up the lowest n over 2 molecular orbitals, cosine of n pi over capital N plus 1. So this would represent the total energy of the polyene for this pi system. And these 2's are going to cancel, so this actually ultimately represents n times alpha. All right, what would I have to compare it with in terms of ethylene? Well, you'll notice that each ethylene has 2 carbons in it, so there are going to be a total of n over 2 ethylene molecules that we need to compare it to. So the total of n over 2 ethylenes would be n over 2 different ethylenes. Each one has 2 pi electrons, and each one has an energy of alpha plus beta. Okay, remember, they're independent of one another, so they'll all have the same pair of energy levels as given here. All right, so what this does is the 2's cancel, and I'll end up with n alpha plus n beta. So now if I take the difference between these two, and I'm going to assume with a little malice aforethought that this is higher in energy than this. All right, so what will I have? I'll have n over 2 times the energy of the ethylenes minus the energy of the polyene. And what this should tell me is what is the relative energy of these 2 different collections of n pi electrons. Okay, in the case of the ethylenes, I'm going to have n times alpha plus n times beta. In the case of the polyene, I'll end up subtracting n alpha from up here and subtracting 2n beta times this sum. Okay, well, these are going to cancel, and I'll end up with n beta times 1 minus 2 times this sum. Now, a couple of things. It's not going to be obvious from this, but all of these terms for up to n equals n over 2 are positive numbers. I'm not going to go into great deal detail about this, but if you were to look at these angles, they basically represent angles like this. Okay, and when we get to the y-axis here for these angles, that's when we go above n over 2. So these are the first n over 2's. And then the next n over 2's are all going to be the angles over here. And we're going to not quite get to an angle of pi out of all of this, because if you look at this ratio, the biggest number we can get is when little n is equal to n, and that will be n over n pi over n plus 1, which is just a little bit less than pi. All right, so this is what these cosines, we're going to get the cosines. The cosine is the x value for each of these angles. All right, I understand if this is not something you're used to or used to thinking about, but this is a way of visualizing what this ends up being. Well, it turns out that, in fact, this is going to end up being larger than this. All right, especially if we multiply it by 2. But we add up the cosine values for each of these angles that I've written here, multiply by 2, and subtract from 1. I'm going to end up with this whole thing being a negative number. Okay, well, that sounds like that polyenes are bigger in energy than ethylene. But remember that beta itself is a negative number. So in fact, this whole thing here is a positive number. And I'm sorry that this is a little bit convoluted, but the whole point is that, in fact, the polyenes do achieve a lower energy. There is a stabilization, and this stabilization is due to the fact that they've connected these ethylenes together. All right, so in fact, what we have here is that the electrons can be delocalized by the pi system. And we've seen evidence of that when we looked at the molecular orbitals, that in fact the orbitals extend over the entire n-atom chain. And this delocalization of the electrons in fact leads to an energy stabilization that we can verify mathematically simply by using the formula that we've already looked at for these linear polyenes. All right, now we could also look at the cyclic polyene case, and I can tell you that it's a really interesting case to look at, but I'm going to ask you to look at it in the problem set. An interesting feature there, however, though, is that the stabilization depends upon the number of carbons in the chain. And in fact, what one finds is that when the number of carbons in the chain can be written as 4k plus 2, where k is some integer, when the number of carbons in the chain is this, that there is a very special stabilization for these systems. That is to say, a much lower energy that accrues. And this is a phenomenon that you're all familiar with, because this is what accounts for aromaticity in certain cyclic polyenes. So you can see that the Huckel theory actually gives us a way to address the existence of aromaticity in cyclic polyenes, but I want you to discover that on your own in the problem set. And if you have questions about that, please feel free to ask.